Okay, so we are going to do about nuclear binding energy first. We had a question as to explain about nuclear binding energy. That was our first question, and it also completes a theory. Okay, write down. I think we had a question called "What is nuclear binding energy?" For that question, no, just as a new topic, it doesn't matter. You can write about what is nuclear binding energy. Write down the first point. When a stable nucleus is formed by protons and neutrons, the final mass of nucleus is lesser than mass of
Is it
lesser than total mass of protons and neutrons. When a stable nucleus is formed by protons and neutrons, the final mass of nucleus is lesser than total mass of protons and neutrons. Now, normally it should be equal according to our general knowledge. the total mass of protons and neutrons should be equal to the final mass. But here the mass is different.
Okay.
Okay. Next point. Nuclear binding energy. Nuclear binding energy is the energy we can calculate. We can calculate
We can
using
calculate.
Using that mass difference. Using that mass difference simply. In brackets, take E equals mc square because that energy is calculated using this equation. Next. In another way, nuclear binding energy nuclear binding energy can be explained as the energy that should supply to separate a nucleus. to its nucleons. To its nucleon. Okay. So it's like, there are neutrons and protons. They get together to form one nucleus. Like this. And bonds are generated between. This energy of these bonds is called the nuclear binding energy. You can calculate the bond energy by now. If a mass of neutron is Mn, neutron is Mn, mass of proton is Mp, and let's take mass of the nucleus. You know, a nucleus is formed basically by neutrons and protons. M capital N, nucleus capital N. So we think, actually, even in chemistry, we think the total mass of neutrons and protons, which gather together to form the nucleus, is the same. The mass of nucleus is equal to mass of protons and neutrons. That's what we think, but it is not like. Actually, if you take the total mass of neutrons and protons, 3 Mn plus 3 Mp is the total mass of neutrons and protons here. This one's mass is Mn. We think it is equal, but it's not. Always the total mass of nucleus is lesser than total mass of neutrons and protons. That some amount of mass is decreased. We learned in nuclear world, mass and energy is not two different things. It's the same. Reducing of mass means, in another way, reducing of energy. That means when neutrons and protons get together to form this nucleus, it gives out some energy. It emits some energy. That energy is called nuclear binding energy. And in another way, that reduced energy is equal to the binding energy between nucleons in a nucleus. So everything is entangled like that. So actually, you can take the delta M, difference of mass, by 3 Mn plus 3 Mp minus Mn. And when you take this delta M to get the energy, E equals delta M C square. You can take that terms. And this is called nuclear binding energy. The higher the energy it can give out, the higher the stability of nucleus. Okay. That's the story. You can take down.
Okay.
Okay. So that's the story there. Then we will go to a new topic. If you can remember last time, there was another question to draw the nuclear binding energy curve. That's the, as I remember, that was the second question. So nuclear binding energy curve, I'll just give you a very simple, not the exact curve. I can send you from a dude some photos and share some photos of the exact curves, but for A levels, we just need to know the idea. Nuclear binding energy curve is someone like this. Yeah, something like this. Units mega electron volt. Here it's A, mass number. Okay. So I have to tell this thing is the element with highest binding energy. Highest binding energy which is iron, Fe. That means it is the most stable atom, most stable. No need to know about others. The stable one is hydrogen actually. Normally iron's mass number is 56, no, so it goes in the the order we know: hydrogen, helium, lithium. Like iron is the most stable, and then again stability decreases. Normally here there will be uranium. But only thing we should know is this. That means iron, Fe, is the most stable nucleus. That's why it has the highest nuclear energy. That's why it has the highest nuclear energy. And here B is nuclear energy, the one we discussed earlier. B is nuclear energy. And A is mass number. So what is B over A? B over A means nuclear energy unit mass number or unit nucleon. That is better. Nuclear energy per unit nucleon. Why? We don't take nuclear energy but nuclear energy per unit nucleon. Why we do that? We do that to generalize, because now if two nucleons get together and form a nucleus, there will be one bond. If three nucleons, protons and neutrons, get together and form, there will be like three bonds. If four, there will be like six bonds. That means when the number of nucleons increase, automatically the number of bonds increase. The higher the number of bonds, the higher the energy, the higher the binding energy. That means the higher the energy it gives out when the nucleus is formed. The higher the number of nucleons, the higher the binding energy. The higher the binding energy. So it is not if the number of nucleons affect binding energy, it is not a good reference, not good detail about stability of the nucleus. Why? It doesn't matter what is stable. If someone has more nucleons, its binding energy is high. Why? Because there are more nucleons, because of the number of nucleons. But it doesn't tell about its stability. It doesn't tell about its stability. That's the thing. So that's why we take the total binding energy. divide by number of nucleons. So here if the energy is E1, number of nucleons is 2. So here B over E means E1 over 2. Here if the binding energy is E2, E2 over 3. Here if the binding energy is E3, it's E3 over 4. Now from this, it generalizes. The effect of number of nucleons cancels off. You always take the binding energy for unit for one nucleon. Then you can compare the stability of the nucleus, because now the energy is higher not because of number of nucleons, but because the bond is more strong. But because the bond is more, or the binding energy is more strong. That's why we should take not B but B over A to compare. That's why we can clearly say iron is the most stable nucleus that forms. That's much more advanced point for A levels. It's not there, but it will come to your exam. They will give details and ask. But when we know it earlier before the exam, then it is easy for us to answer. As these actually are somewhat extra, but not totally extra. It's good to know this. That's it. That's everything. There are many more things about binding energy, but for now, for A levels, this much is enough. You can take down the sketch and everything and finish. This one is not needed, just the graph is in. Okay. If this is finished, we can go to the next part.
No.
Okay.
Finish.
Then next one is about nuclear fission reactions. I think the questions also, next question was about nuclear fission reactions. The meaning of word fission is breaking. Nuclear fission reactions, or just nuclear. Right down.
Reactions.
Yeah. Nuclear fission is the process where a particle or nucleus, a
Particle.
particle or nuclear. Is used is used to collide with collide with a large mass atomic nucleus and break it into parts. Which forms enough energy, or which forms energy. Example equation: uranium-235 is attacked by neutron. This is a nuclear power station, and first it will become new uranium-92 and mass 236 by absorbing the nucleus. Then it's unstable and it is breaking into barium. There are other reactions also. I mean, it can break for others also, but I'll go in a more common path. 141 krypton 36, sorry, krypton 56. No, and mass 92 plus it forms 3 more neutrons. That's very important. That means, and energy is formed. This energy is used as nuclear energy, and it forms 3 more neutrons. That 3 more neutrons attack another 3 uranium atoms. It forms 9 more electrons. Like that. It's like these are called the chain reactions. One neutron again do a reaction and form another 3. So it's like how bacteria increases its number. It's like it's a chain reaction that we cannot stop. It goes and make more and more neutrons and make more and more collisions and produce more and more energy. That's what important there. That is, and we should control the rate of reactions by controlling temperature. We have to do a very good cooling for nuclear power stations. Otherwise, these chain reactions become unstable and it becomes a nuclear bomb. There's a very small difference between nuclear power plant and nuclear bomb control. If you control the temperature and keep the rate at a certain point, you can use the energy efficiently. But if your control goes out and vulnerable, it becomes vulnerable, it becomes a nuclear bomb and it blasts. Things happened in Chernobyl and some other nuclear plants. So cooling is a very important thing to keep the chain reaction rate constant under a certain value. So that's it. That's the story. Normally, this is what we use in nuclear power plants. I mean, nuclear fission reactions are what we use in nuclear power plants, nuclear power stations, power plants. But as I said, if the control becomes vulnerable, if the control destroys, it becomes nuclear bomb. There's only another one thing we should know about this. Why neutrons are used? Why we don't use any other type of particle? Only that I want to discuss. You can take a question, you can add a question there. Why we use neutrons? I'm saying I'm telling you the question answer, but you have to write it later because this question will be there in A levels. You have to memorize it and write. So I'll only tell you why neutrons are uncharged particles. So there will be no any other effect on it. Like there will be no Coulomb effects, like from the electrons of the atom, it will not repel when it goes to if it has a charge, the with the atoms electrons or then protons, it will interact. But if you use neutrons, they have no charge, so they don't interact with the atoms charges. So because they don't interact, their process, their work is not get affected. That's why using neutrons is better and important. That's right. Okay. Then that's all about it. Let's go to the next topic. The next question I gave was about nuclear fusion reactions. Nuclear fusion. Let's discuss about nuclear fusion reaction. Fission means breaking. Fusion means addition or get together. Fusion. Fusion. Nuclear fusion reactions. Write down. It's the opposite type of nuclear reaction. Write down. When lighter nuclei get together to form a middle mass nucleus. Middle mass nucleus. In brackets, you can put A equals 50 to 100. It emits energy. Emits energy, which we call nuclear fusion energy. Which we call nuclear fusion energy. Okay. Next point. For the fusion of two nuclei, for the fusion of two nuclei, the Coulomb repulsion, Coulomb repulsion should be withstand, should be withstand for that neutron, for that
For that,
for a very big temperature, very big temperature, like 10 to the power of 8 Kelvin, like 10 to the power of 8 is needed. Next point. That is why it cannot be done. Cannot be done. On Earth, but only happen in sun or star. Only happen in stars. Sun is also a star in stars. So naturally, it happens in stars. It's very hard to do it. Still, it cannot be done on Earth. Because how can we give a temperature like 10 to the power of 8 of kelvins? For now, it's unrealistic to do on Earth. Mm. Okay. But there's another thing in another way. No, we can't do it. That's correct. But in another way, this makes more energy. You can put it. You can take it down. Nuclear fusion generates more energy, more nuclear energy than nuclear fission. That's the story. There's we can't write nuclear fusion reaction with only one example. There is a range of reactions Now in the star, no need to write it in. We don't need to know that in sun or in stars, hydrogen get together and form helium. And basically that fusion reaction forms energy. Uh, if there's any extra knowledge, I mean, this is totally enough. But if you want any more thing, I'll send you as pictures. Otherwise, everything is finished. Yes. Yeah. Lesson is finished. Okay. Fission and fusion is the last one. I gave another question about that mass, but it's totally outside the syllabus. So I'll just show you some photos or something or pictures of that, and no need to write about that may masses. Yeah, the unit is finished. Matter and radiation. Then I think your whole syllabus is finished. Yeah. Then I think you have another like 3 months for the exam, so you can
Okay,
decide.
doing it in February.
Sorry.